morning, class. Today we're going to be talking about quantum numbers. So let's start off with a little refresher. So we have three different sets of quantum numbers. So we have our n. Our n represents our principal quantum number. So this is the distance from the electron to the nucleus. Next, we have our secondary quantum number, which is our L. Our L is our angular momentum. So this is the shape of the orbitals. So I have this chart here that tells you if L equals 0, it's going to be in our S sublevel. And 1 is L, that's going to be in our P, and so on. And next we have our ML. Our ML depends on our L, and our L depends on our N. So our L is always going to be the N minus 1. So if our N is 4, our L can be 0, 1, 2, or 3. And then our ML depends on which sublevel the L is in. So let's start off with our first example. We're going to be labeling the following quantum numbers as allowed or not allowed. And then we're going to identify the problem. So first off, we have our N equals 2, L equals 2, and ML equals 0. So first off, we already have a problem here. We have our L equaling as the same as our N, which what we just said is our L always has to be N minus 1. And if we have our N equals 2, 2 minus 1 isn't 2. So what this means here is that we'll have a full sublevel in 1s, a full sublevel in 2s, a full 2p sublevel, but then we reach a problem. Because when we look at our L equals 2. If it's 2, then it's in our D sublevel. There is no D for our second sublevels. We do not have a D here. So there's our problem. In order to fix this, we could do N minus 2 is 1, so this could be our first sublevel. And if N is 2, we're looking for our 2's. If L is 1, we're looking for our P. And if ML is 0, it'd be negative 1, 0, and 1. So it would be this one, if that was the correct way. Our second example, we have N equals 2, L equals 0, and ML equals negative 1. Our problem here is that our ML is dependent on our L. So if L is 0, ML must be 0. So what this is saying is that we're looking for our second sublevel, which is this one. And if it's 0, it has to be S, as we have here. But there's only one option here. This can only be 0 because there's only one option. But it's saying negative 1. So we have something here that doesn't exist. So we can't have that one. Our next example, N equals 4, L equals 0, and ML equals 0. So it's saying we're looking for our force. We have one right here. 0 is our S sublevel, which we have here, and our ML is 0. Which we just said, if L equals 0, ML equals 0. So that means we have a full shell up to this one. So this is what C represents. So C is good. And our last example we have is N is 2, L is 3, and ML is negative 1. So we're looking at our principal quantum number, which is 2. So it could be any of these two. But our L is 3. And this doesn't make sense because our N is 2, but our L is always N minus 1. Because this is our secondary quantum number. So it's always going to be 1 less. So if our n is 2, our L can only be 0 or 1. We can't have an L of 3. So what this is saying is that if n is 2 and L is 3, we're looking for an F sublevel. But we don't have an F sublevel with our 2 quantum number. There's no such thing. We only reach our F sublevel when we get to, we're looking for a 3, then our principal quantum number has to be a 4 or higher.